Welcome to Correlation Part 1, a tale of two equations. And those two equations are going to be for the correlation coefficient. Now, if you've taken a course in statistics, you may remember seeing a formula that looks slightly like this for correlation. This is one of the correlation formulae. I'm not too fond of it. I seem to remember seeing this for the first time in my own stats course, and it was slightly traumatizing. It just didn't quite look friendly or very revealing of what a correlation coefficient was or what it did. However, this is one standard, perfectly good equation for the correlation. What's wrong with that equation is that it is a computational equation, what I will refer to as a computational equation and contrast with a conceptual equation. Now, computational equations are perfectly good. They're very helpful for computing answers by hand involving a large number of observations, but they can be opaque as to their meaning. Mathematicians, including statisticians, come up with computational equations because they make, like I said, hand calculations easier, and that was very important before the advent of good handheld calculators and the computers that we have around today, which rendered these computational equations perhaps a little bit less useful than they used to be. Computational equations can be compared with conceptual equations. Conceptual equations are often elegant, clear expressions of what a statistic means. These conceptual equations help us understand how a statistic works. Now, they may not be the easiest to work with by hand to compute for example, a correlation coefficient with a large number of observations, but they are, like I said, more transparent as to what the mathematician, what the formula is trying to get at. So now here is the computational formula we saw before to the left for the correlation coefficient, and to the right is the conceptual equation for correlation. And you'll notice that it is a lot simpler than the computational equation. What it says is that the correlation coefficient is equal to the sum of the cross products between the z-scores on test X and the z-scores on test Y divided by the n of the sample. Now, I find that equation to the right to be a lot more friendly than the one to the left. Of course, you can use either one because they're algebraically absolutely equivalent. But like I said, I like the one to the right, and if you know how to calculate a z-score, this is going to be an easy formula to use as long as your n isn't too large. If your n is large, well, I suggest that you use a computer software to calculate your correlation coefficient. So when I show you here how to calculate a correlation coefficient, it will be, what we'll do first is to calculate the z-scores for two tests, test X and test Y, and then we will use this formula for the correlation coefficient. And that's it for now.